So in this revision video, we're going to be looking at copper and zinc chemistry, and these will be our objectives for today. So we're going to be looking at copper and we're going to be looking at zinc. So copper and zinc are found here in the periodic table. They're found in the D block of the periodic table, and their electronic configurations are. So here are the electronic configurations of copper and zinc according to the periodic table. Now, due to stability rule, which says that half-filled or fully filled subshells are more stable, right? Because of this, what will happen is 4s will give one of its electron to 3d, so the electronic configuration actually will look something like this. Now we can see 4s is half filled and this is fully filled, so it's much more stable. Alright, so this is the electronic configuration. And yeah, now notice we have the definition of transition metals. Now, transition metals have partially filled the subshell. That would be responsible for the following things that transition metals have. They have colored ions, variable oxidation state, and catalytic activity. All of this is because they have partially filled d orbital. But now notice here that zinc actually has a complete d orbital. So we will see zinc is a bit weird. It doesn't show the things that a transition metal is supposed to show. So you're going to be seeing what zinc does and how it reacts and how is it different from the other transition metals. And really, we don't really consider zinc a transition metal actually. It's still there because it has a d orbital. It has a d subshell orbital, but it doesn't behave or it doesn't fall under the transition metal definition that we have. So both zinc and copper are d block elements, but zinc is not a transition metal, and on the other hand, copper is a transition metal. So while both of them are in the d block, one of them is not a transition metal and the other one is. Is zinc even a transition metal? Well, of course, it's not a transition metal, so no. Now, one of the major things we'll see in reactions of zinc is that zinc is always colorless. It forms zinc 2 plus with the electron configuration of Ar 3d10, where the 2 electrons removed are from 4s. And yeah, and if further electrons would be removed, they would be removed from 3d. But the stable ion that zinc forms is Zn 2 plus, right? Now notice dd orbital splitting occurs here. Yeah, that happens. But the problem is not that dd splitting happens. The problem is that when you shine light, so let's say you have this sample and you have zinc 2 plus in it. Now when you shine the light through the sample, what's going to be happening is that light will pass through it, but there will be no electron that could move up to the next level. Because you see, for an electron, let's say this electron, when it wants to go up, there has to be some space available, but there's no space. So there will be no electron promotion. No electron promotion by gain of photon. So that's what's going to be preventing that color from coming in. Right? Now, dd splitting will happen because we're going to have ligands that are going to be attacking zinc and forming native bonds. So that's going to be happening, but the electron promotion is not going to be happening. And because of that, whatever you're going to see of zinc, it's either going to be a white PPT and colorless. Right? So that's a very important thing to know. Now for copper has color. So copper has color. Okay? And the ions that copper forms is copper 2 plus and copper plus. For copper 2 plus, it has color, and we're going to see it as well when we go to the reactions. Copper plus is colorless. Okay? Copper 2 plus is colored, it has color, and copper plus doesn't have color. So this is an important point you have to keep in mind. and they will want you to know the explanation behind this as well. And actually the explanation for copper plus is very similar to the explanation, or actually the exact same explanation that there is for zinc 2 plus. Same explanation, but it's better if I show you. So let's see it. Now, we're going to be seeing hexa, aqua, copper. So we have the water ligands which have formed dative bonds with copper. So the coordination number here will be 6. Okay. And because these ligands have attacked copper, they've caused the d orbital splitting, and copper is 2 plus. So this is for copper, and this is for copper 2 plus. Notice something very interesting here. One electron got removed from here, and then one electron got taken from the 3d10. Okay, so 3d10 means that 10 electrons, one of them goes away, so it becomes 3d9. Now, when the d splitting happens, there is an energy gap, and if the photon's energy corresponds to this energy gaps, if photons, so the change in energy or the energy gap should correspond to the specific frequency of the photon, so they both should match basically, and this will cause the electron to be promoted. And notice there is space, so electron can easily move up as well. And then the transmitted frequency of light is the reason for color. Now, this will not happen when we have copper plus. Okay, so this will not happen when we have copper plus. So for copper plus, if you see, we have, this is our copper electronic configuration, AR. Then we have 3, let me just write 4s1 3d10. And then if we go copper plus, we have the argon, and then we have 3d10. So you can notice that the d orbital is completely filled. So even though the d splitting will happen, there will be no electron promotion because there is no space available for the electron to be promoted and move to the energy level that the orbital that has higher energy, right? So it cannot move to the orbital that has higher energy. From the lower energy to the higher energy, it cannot move to that place. So because of that not being able to happen, because of electron not being able to be excited, that will cause copper plus to not have a color. Okay. Now each of these reactions will work like this. I'm just gonna give a quick layout of how all of these reactions will occur. So first we'll always have deprotonation, and then we'll always have the ligand exchange. Okay, and then if there's anything else, I'll let you know. Okay, so we're always going to start with hexa aqua. Okay, that's going to be the starting point. Hexa aqua zinc. That's going to be the starting point. So we're going to have our zinc H2O6, which is going to be a colorless solution. And let me just put the charge there as well. So that's going to have a +2 charge. So when you add drops of NaOH, what happens? So here I've written all of the reactions down. So we have hexa aqua zinc reacting with drops of sodium hydroxide. So we can see that there are 2 hydroxides that are going to react and remove that +2 charge. And then we're going to have this right here, which is going to be having, this is going to be a white precipitate. And this is going to be dihydroxyl tetra aqua zinc. Alright. So this is going to be white precipitate here, plus 2H2O, and this is going to be deprotonation. Alright. Now you can actually reverse this, so you can take your this white precipitate and you can make it react with 2H plus, and you can make it go back into the colorless solution of hexa aqua zinc. So that is possible, and that actually shows us the amphoteric behavior. That shows us the amphoteric behavior. Okay. Now, the same white precipitate which reacts with the 2H plus can also further react with 2OH minus, right? So it can react with H plus and go back to the colorless solution, and then it can also react with 2H minus further to give us tetra hydroxo zinc. So we can have this forming, and this is going to be again colorless solution, right? So if we add further excess of NaOH, then this further reaction will take place, and this will be ligand exchange. All right. So this hydroxide here can react with both acid and the alkali as well. So that's why I told that it is amphoteric behavior. It shows amphoteric behavior. So we can see that we have our drops of NaOH, and then we have excess NaOH. Now, similar thing happens when you have zinc reacting with ammonia. It's going to go from colorless to white precipitate first, and it's going to be deprotonation reaction, and it can go the other way around as well. If you add 2 H plus, let me just put a 2 here as well. So if you add 2 H plus, and then this here can also react with NH3 as well. So it can react with the acid, and it can also react with a base. So it hence is also amphoteric in its behavior when it comes to reacting with acid and alkali. And then again, your zinc, the white precipitate of zinc, if you add further NH3, it will react, and we'll have zinc, and then we'll have 4 NH3 here, and then we'll have the 4 water molecules, and then we have 2 OH minus molecules there, and this is going to be ligand exchange. Alright, so that's pretty much all the reactions. So I recommend understanding them and memorizing them as well. Okay, and yeah, so the key things here is precipitate always never have charge, and for zinc, zinc is actually the zinc and I think chromium. Those are the only two ones that react when you have they give some sort of reaction when you have excess NaOH, right? So you have to memorize this. So keep these in mind. Next, we're going to be talking about hexa copper and tetrachlorocopper as well. Right, so we have another reaction here where we have tetrachlorocopper, and that's going to be when you add that in water, you're going to have hexa copper, and then you have the 4 chloride ions, and the reverse can take place below as well. So it's just the same thing, but just reverse. Okay, so when you add tetrachlorocopper, which is actually a green solution, it becomes into a blue solution, and then if you take this blue solution and add your HCl into this, which will supply your chloride ions, and you must make sure the HCl is concentrated, then you're going to go from your blue solution back to your green solution. Now you'll notice why do we only have 4 chlorides that are attacking and forming the dative bonds, whereas we have 6 water molecules that are water ligands that are attacking and forming dative bonds. Well, that's a past paper question, and that has to do with the size of copper, of chloride. Well, that is because of the size of the chloride. Ions are very large, and they cause steric hindrance, which is basically if you take copper and we try to fit in 6 chloride ligands, they'll just repel too much, and that's basically what steric hindrance here is. So only 4 chloride ligands will attack, right? So that's all for this part. So we're going to be starting off with hexa copper again, and hexa copper will react with your drops of NaOH to give you again the same thing that we saw before, but instead we have copper now. So this is going to be dihydroxo tetra aqua copper, and then we have 2 water molecules right there. So this is going to go from blue solution to your blue precipitate, and this is going to be deprotonation. If you add excess NaOH, nothing is going to be happening. And the same thing happens when you add your drops of ammonia as well. Again, ammonia will react with the hexacycle copper, and there will be deprotonation reaction. So deprotonation will occur. So these are also called the deprotonation acid-base reaction as well. And then with excess, yep, the reaction will happen in excess this time. The reaction will look something like this. We'll have 6 ammonia. Now, out of these 6, 4 will be forming dative bonds with the copper, and the other 2 will be used to remove hydrogen from the water. And when the hydrogen of water is removed, they will form 2 ammonium ions. And the other 4 hydroxides that were formed would be replaced by the 4 ammonia, and that's why this is called the ligand exchange. Alright? And then the solution will go from blue precipitate to deep blue solution. I'm not going to explain too much in detail because the video is already pretty long. So this is revision again, but even revision I like to explain in detail, but yeah, so that's all.